Okay, welcome to this lecture. So before we start, I just want to make sure that everybody is here for the Vigyan Vidishi lecture and not for the asset colloquium talk, which is happening right across the hallway. All right, so we are very happy to have Rijurekha Sen here today from IIT Delhi. Rijurekha is an assistant professor in the CS department there. Her research interests are broadly in problems at the intersection of information technology and society, and in particular on things like building distributed, networked, and privacy-aware systems. This includes her work on building systems for road traffic monitoring, human mobility measurements, public policy audit, and privacy enhancements in ubiquitous system. Before moving to IIT Delhi, Rijurekha did her PhD here at IIT Bombay, so she's familiar with the city. And she spent parts of her postdoc years at the Max Planck Institute for Software Systems at Saarbrücken. Okay, over to you, Rajuri.
So I'm going to talk today on this topic on sensing for urban sustainability. And urban means, of course, our cities like Mumbai and Delhi, where we spend a lot of our time. And sustainability means that how to make these cities more livable or more manageable. And sensing, we'll see that it can mean gathering more information about what's going on in the city. And this started this kind of field of work is relatively new as a computer science discipline, and even the conferences like menaces or census or movicom, these conferences are relatively new. So in 2006, one of the first papers came from MIT, from the group of Professor Hari Balakrishnan, who thought that maybe if we build a system called Cartel, where each car has some sensor. Now we know that GPS is ubiquitous in all our cars, in all our motorcycles, and we have Google Maps. This was before that era, but he came up with this idea that if cars could sense where they are and they could somehow transmit this information to some central server, then a city could build this kind of congestion maps, which we now see as a regular Swiggy delivery app or any Uber, how long it will take to reach us, or even when we are traveling on the road, how long it will take to reach somewhere, right? So this was something where we thought that sensing an information that this at this particular timestamp, at this latitude and longitude, the car is here. And as the car is moving, it keeps on sensing its own position, and either itself does some calculation or it sends this to some central server, which accumulates this data from multiple sensors across the city. Similar very good quality work came up in these early years from Microsoft Research India, where they thought that the quality of roads or the driving behaviors, it could be monitored with sensors like accelerometer and gyroscope. And if we put them again on vehicles, then they measure the vibration of the car, whether the car is braking or not. And based on those things, we can decide that whether a city has a lot of potholes on its roads or whether the driver is harshly driving the car on. So, of course, we now know, as we were discussing, that it has been having a lot of real life impact when with all the maps that we have. We cannot even imagine our lives without this kind of sensing these days. And even the kind of systems with Microsoft Research India was building, they are part of many insurance packages now, where companies like Zendrive, they monitor the drivers of the cars and their driving behaviors to decide whether to give that particular car insurance claims or not if they meet with an accident, right? And in fact, things have moved beyond so much that our cars are so instrumented that we now say that maybe we don't even need a driver to drive that car, right? It will sense itself. It will have radar, it will have LIDAR, it will have cameras in all directions. It will do deep learning, reinforcement learning, LLMs and all those things. And then it will decide where to drive, right? It will decide that, okay, this is an obstacle, this is this. So these are self-driving or autonomous driving systems, right? So this is kind of like in 2025. And now you are in Mumbai, now currently attending Vigyan Vidushi, and it might seem a bit fantastic because maybe in case of India, we are still stuck in this traffic, right? I mean, we are thinking of, on the one hand, in terms of technology, we are thinking that cars will drive themselves, but where will they actually drive, right? I mean, we are still stuck in a lot of traffic jam. And even if Google Map is showing somewhere in 1 hour, maybe the road is so waterlogged that it is taking 1.5 to 2 hours to reach a place, right? So there is some sort of a disconnect, of course, between the actual real world or the real cities that we live in and somehow the fantastic papers or the systems that kind of tend to come out in the research conferences. So this is, of course, all good, but then the question is, where is the computer science in all this, right? We understand that we will need to have better public transport in a city. We need to reduce our dependencies on private vehicles, and we have to build more roads and flyovers to create alternative routes so that our congestions come down. And then we also need to see how budgets are allotted, right? As in a city, how much of our budgets are going in building this kind of infrastructure. And sometimes we wonder that we are computer by training, we are learning computer science, and maybe these are all work of civil engineering or transport and engineering or some other department, right? So this is where I'll try to motivate that computer science matters everywhere, and we can use the tools which we learn in very real life problems. Okay. So, being a Bigyan Vidushi talk, if I would sit there, I mean, maybe you are an undergraduate student right now, maybe in second or third year, and at least for me, I did my UG and then I went for a job, and my choices were not driven by the problems I want to solve. Right. I mean, neither technical. So mostly everyone was giving J. I gave the J West Bengal joint entrance, and then computer science seemed to be giving good job options at that time. There was no AI taking our coding jobs at least, and therefore this was a natural career path, right? And this was it had nothing to do with the real life problems or even theoretical problems which I wanted to solve, right? So the career path of school and then undergraduate in computer science and then doing a job was mostly driven by the market forces. But then in IIT Bombay, I had an excellent PhD advisor, and his name was Professor Bhaskar Raman. And he not only kind of taught me computer science skills, system skills, computer networks, operating system, computer architecture, which are my core skills till now, but he also kind of gave me books to read and like Jared Diamond's Collapse and things like that, and just tried to make me think that maybe we as engineers or as technology people, we can be more involved in problem solving, right? So he has been very instrumental in that. And in my PhD, this is just a short description. It was around in 2010, 15 years back, that I was building systems for traffic measurement. And the idea was very simple, that there was this wireless transmitter. So this was, suppose, one road in Mumbai, and there was a wireless transmitter which I put on one side. It might be a Bluetooth or a Zigbee radio or a Wi-Fi radio. And then there was a receiver on the other side, right? And maybe you are already doing Ram Prasad's course on error correcting codes and those things in this summer school, and and we can decide that if the sender or wireless sender knows what packets it is sending, the receiver can check for errors in those packets, right? And here, the errors were being caused by the vehicles which are in between the two kind of nodes, the sender and the receiver, right? And we saw that because of interference, because of scattering of Wi-Fi in the physical signal space, when there was more traffic on the road versus when there was less traffic on the road, there was clear distinction in the quality or the received signal strength of the wireless packets. So this is a graph where on the x-axis, I see the received signal strength, and the this side or the right-hand side is better signal strength. So this is the value of -55 is a very good signal strength, and -95 is a very poor signal strength. And the y-axis is a CDF, and the CDF is computed over packets received over a time window. And this time window is taken as 5 minutes of time. And each graph here, each curve here, as you are seeing, is say I start measuring at 5:37 in the evening, and at 5:42 p.m. This is the first curve, this is the second curve. So each of these curves belongs to 5 minutes of accumulated packets at the receiver and the signal strength of those packets. So if you look at it, when between 5:30 to around 6:20 p.m., the received signal strength was pretty good because the office time traffic jam had still not come in. And in between, there was one line here where something was intermediate. And then starting from around 6:30 p.m. to 7 p.m., the signal strength was really, really bad. Almost all packets were lost, and whichever was received at very poor signal strength, right? So this is a very simple sensor which costs around 200 rupees, and I could put it across the road and build a very cheap mechanism, and it did not require the lighting conditions to be good, which is typically needed in case of a camera, right? So you cannot work well in case of fog, you cannot work well in case of rain, and this kind of radios, they can work even at night, right? When the office peak hour is again there in the evening. So I could build a system, and I built upon it in my PhD, and I did a lot of deployments in Bangalore and places like that. So this is what I mean by sensing. So sensing means I'm trying to sense some information from the road, which is how much traffic is building up on the road. And I need to use some mechanism, right? Some sensor to do this. And here I was using wireless radio. So along with the sensor, typically the flow of work, which I have been doing since my PhD, is like the graph I was showing you in this slide was like a proof of concept, right? I just go and pick two sensors, and then this is the proof of concept graph that this sensor actually works to decide between at least two traffic states of relatively empty road and a congested road. And then once we have a proof of concept, I cannot sit on the road with two radios all the time. So typically we would build hardware prototypes, right? We would put together microcontroller, some memory, some SD card, some radio to communicate this to some server. So there will be some embedded device which will be built. And then deploy that again on real roads and test it against ground truth. So ground truth would mean that there would be actually cameras again, because I am proposing something different from a camera. And whatever the camera is seeing, my sensor pair should also see that. So this is typically something that when I propose a new sensing mechanism, I have to validate it against some ground truth. Okay. So, and what is the quality of the ground truth? There should be some human labeler who also have to agree on that ground truth, that what is the traffic situation on the road. So this is typically what happens, and this happens even now. So this is a different picture from my work at IIT Delhi, where we put pollution sensors, air pollution sensors on all Delhi buses. And this is the first batch of prototypes which we built, and we tested it on buses for a few months. And then based on our experience on what worked and what didn't work, this is the second batch of prototypes, right? So this is when we build hardware, we first have to be confident ourselves before we go out and talk to governments to adopt it and then sense it. So this is prototyping, prototyping and testing. This goes on iteratively unless we are pretty confident about the product that we have. So the motivation on computer science tools, of course, building an embedded system has some engineering aspects. Now let's discuss concretely that what other ways can computer science help in this problem. And the first constraint which we have in a place like India, which we call as a developing country, is budget, right? So when you have a city and you need to set up some infrastructure, there is specifically some budget to do that, right? And if you put cameras, if you put whatever sensor we put, we have to plan that appropriately. So one way of generating money in Delhi has been this vehicle challan application, where when vehicles break rules, we fine them. Right. And there are several companies with whom we work, because the Indian traffic is kind of very non-lane based. And even if you have a speed gun or a radar which has detected a speed violation, doing the OCR and giving the challan sometimes has legal repercussions. Right. So how the computer vision models work well is something which needs to be built. But as a result of this computer vision, which comes from the computer science domain, a lot of money gets generated for a government. Right? So which helps in the budget problem. And once we have that kind of budget, it can be used for other applications. So here, for example, we have cameras for Chalan, but the same cameras, and these have been deployed by actually two companies across Delhi NCR. One is Behant and one is Armatica. And you can use the same cameras now to not just give chalans, but also detect traffic density, right? Which, like I was doing in my PhD days, now the cameras are already there. Of course, you need some infrared support or some support at night to have night vision cameras. And then you can detect that, okay, when the signal turns green, the density of traffic starts coming down. And again, when the signal turns red, this density keeps going up. And some of these computations, can use other computer vision algorithms like background subtraction or optical flow, again, computer science subjects, which also we can compute on the CPU, right? So when I'm talking about any computation like detecting a car using some more complex machine learning model versus some simple algorithm where I just subtract a picture of the road continuously, we can decide on the embedded hardware to use, right? So the platform that we will build, whether we will need a GPU or a graphics processing unit there, or a CPU is enough, like what is present in our laptop on our phones, whether that will be able to do the work or not, that depends on what kind of computer vision algorithm is working there. Okay? So this is some work where budget can be generated using these files, and then the same budget can be, the same cameras can be used for other applications as well, like detecting the density, and I will show how to use those density numbers in a few slides. Now, the second constraint which comes other than money is the absence of ubiquitous network connectivity, right? So it's not like all our Indian roads are connected by fiber connectivity, which is like taking the camera videos from the road and send them in real time to some Amazon server or some Google server where all the expensive or heavy machine learning algorithms can run, right? So this is there is connectivity, intermittent connectivity, of course, and then there is 4G connection or now upcoming 5G or 6G connections, but they are costly, right? So you need to keep on recurring bills to Airtel or Vodafone, whoever is the backbone of that network. So there is also this need, and that's where these companies who are working on the ground work with professors like us, where they want to push a lot of computation to do on the roads itself, right, or in the buses itself. So they say that instead of sending the raw data, real-time videos all the time to some central server, can these be processed on the road to some extent, right? Some information maybe needs to be centrally seen because, for example, for intersection control, I cannot just control one intersection at a time, right? It might create some chaos in some other places. So there needs to be some centralized thing sent, but it might not be the raw videos that we have to send all the time. Right? So this is the second constraint after budget, that the absence of network ubiquitously. And here, it's a very big topic of running machine learning or some heavy computation on edge platforms, as we call them, right? Whatever we put on the road or on the bus, we call it as an edge platform, not a cloud platform, because this is closer to the edge of the network, right? And this is a example course which I took at IIT Delhi when I joined in 2018, where there are different aspects of this optimization. That there is some computer vision algorithm which needs to run on a smaller platform, which does not have many GPU cores, right? Which might need to run some things on the CPU, and therefore you might be learning again in your summer school some of these topics. This topic of neural network compression, which Jatin might be covering, where there is some sparsity which we can exploit and have some cheaper model and cheaper sensing, which is more efficient, right? So it can come from compressing a neural model, learning smaller neural models or machine learning models, or it can also come from optimizations on the system software side, that the compilers which compile these neural models and make them run on CPU or GPU, those compilers can be better and more intelligent. We can have better runtime control. right? And see that what needs to be scheduled when, which task is more important, so there can be work there. So this is a sample course where we see that not just on the machine learning algorithm side you need to do optimizations, but there is the full stack you can optimize, right? You can optimize compilers, runtimes, and stuff like that. And in this aspect, the kind of work which is important, especially in academia, because if you see that these edge platforms on which we run these computations, if we want to put something on the road, we have to decide that whether it's a CPU or a GPU or an FPGA, or whether it will be some specialized hardware accelerator. Right. So this comes from the knowledge of computer architecture, that what kind of a processor core do we have, right? And what is good for what kind of application, which one heats up more often, right? So when we run something continuously on the road, and which if it is 45 degrees Celsius in Delhi or in Mumbai, will that burn the GPU, edge GPU platform, and whether an FPGA is better or not? And then the whole software stack, which comes from multiple companies. So the hardware companies give out this hardware, and they each have their own software stack. So measurements are very important in a sense, even to understand that given an application, which hardware and which system software stack is doing what, right? So this is one way of doing research, that you take a very complex ecosystem as shown in the picture here, where there can be different hardware choices, different software choices, and then different applications to run on them. And another important thing to have, which is good to the way my group actually deploys these cameras or pollution sensors across the city, we have kind of in-house data sets, right? So if we look at the example we saw earlier, this is an example of measuring this traffic density on Delhi roads. And this particular graph is an extended graph over, say, 2 months, right? A longitudinal graph, where the x-axis here for each plot. So these are 3 approaches on a road. So this is approach 1, approach 2, approach 3, where by approach, I mean this is a 3-way intersection. It's called Lajpat Nagar in Delhi. And in this 3-way intersection, this is each of these is an hourly average of traffic density over around 2 months, right? So this is an hour of the day. This is 7 o'clock in the morning, and this is around 9 p.m. in the evening. And if you look at it, the traffic density on this road, it varies from 0.6 to 0.8 at 7 o'clock in the morning. It's not like that congestion sets up at exactly the same time of the day every day. And over those periods of 2 months, there is a variability in the traffic density on that particular approach. And on one approach, we see a morning peak as well as an evening peak, whereas in the other approach, we see only a evening peak and no morning peak, right? And if this kind of empirical data set is actually available with the research group, then it can help, as we will see, both in designing machine learning algorithms as well as system softwares, because we don't need to run everything on the GPU at high frequencies all the time. We can shut down tasks for bit of thermal safety and keep the GPU platform cooler, right? So these are 2 important aspects of the research that my group is doing in this domain, that understanding the complex hardware and system software ecosystem, as well as using the data sets that our group has been collecting, and then using those to build better machine learning algorithms. And for example, you can go and read these papers more in more depth. So for example, this is intersection control using reinforcement learning, where, as we said, that we can do a lot of optimization in throughput and travel time, because the traffic densities on all these different roads have a variability in across days, right? And we should not have a 5 minutes, 3 minutes, 5 minutes kind of a traffic signal cycle at all times of the day. So this can be built easily if we have access to real data. And similarly, these 2 points of how to optimize energy or temperature of a platform, these also have used these real data sets, whereas this compiler measurement and performance modeling, these set of papers kind of are more measurement papers of the hardware software. Okay. So I'll now move from the traffic kind of example of urban sustainability data sets that our group is collecting and move a bit to the air pollution side where there has been some work. So this is a problem where I would say budget or network or thermal safety are not pressing problems. This is the problems that we have been discussing. So air pollution is so important in Delhi and everyone talks about it that it has a lot of budget already given to it. Network is not a problem because pollution data, the air pollution values are not as many bits in information as the videos which come from the traffic intersections. An intersection having 16 cameras or 32 cameras sending the video in real time needs much more network bandwidth than pollution PM 2.5 value, which might be intermittently collected every 15 minutes or maybe even after every second. And so once this is the kind of scenario, this is the another sensor which is important in the pollution domain, and it is very similar to the traffic sensor which I was describing, which I had used in my PhD days. Just that now instead of putting this sender and receiver across a road, now there is a sender and receiver within a small instrument, right? So this is a particular small device which sends a laser beam. Again, there is a sender and a receiver. And based on how much particulate matter is there in the air, right? How many granules of dust and other particles, PM 2.5, PM 10 is there, that laser beam has some, it is diffracted and the angle changes. And that change of angle is then calibrated or made proportional to how much particle is there in the air, right? So this is the sensing mechanism is very similar, that if there are obstacles, something will get diffracted or scattered, and then that change can be calibrated to sense that phenomena, right? In case of my road traffic, it was vehicles which I was measuring. Here I am measuring the PM 2.5 or PM 10 levels. And because, as I said, budget is less constrained, now we can instrument, for example, in Delhi and in Kolkata, there have been many large deployments in the schools and colleges and public buses of these kind of sensing platforms, right? So where I can gather information in real time of the PM 2.5 and the PM 10 values. Of course, there has to be some decisions on how to take power from the bus, where to put the sensor and all. And then we can build a network like this, right? So this black dots, which I'm showing here, are very expensive crore rupees instruments, which are set up by the pollution control boards at the national level or at the state level. And then green ones are low-cost static sensors deployed by my group. These can be in schools and colleges and other places where we are permitted to work. And then this kind of trajectories are the public buses, which are traveling across the city all the time, right? And once we build this, these are, for example, some data sets collected by my group. There is also this question of calibration, right? So as we were talking that when Ram Prasad talks about this error correcting codes, the sender of a network packet knows what it has sent. And therefore, it is possible to detect that error in the receiver, right? And that is true in a network communication. But in this case, where I'm sensing something using a lower cost sensor, I don't even know what the real value is and how to correct for it, because there is no actual real sender who knows the correct value. So here, for knowing this correct value or ground truth, we need to do some deployments as shown in this picture, where we put our sensor, the low cost sensor, very close to the CAQMS, which is a crore rupees instrument deployed by the government. And there are very few of these across the city, right? And once we deploy it, what we see is, so this orange line is the low cost sensor here in Kolkata. And there is a blue line somewhere in the CAQMS, which is the high cost sensor. So in Kolkata, where the relative humidity is high, we see that our low-cost sensor always overestimates pollution, because absorbing the water molecules, the kind of the dust particles blow up, and then our laser beam gets more diffracted, and therefore it overcomes, right? The problem is not so prominent in Delhi because relative humidity there is much lower, and the orange line and the blue line matches more closely. But in either cases, it is good to calibrate the low-cost sensor, right? So this is always a kind of a repeating topic where we do sensing, where we have to do corrections, right? Because the phenomenon we are trying to sense at a lower cost, at a cheaper cost, it might not, the sensor might not be as good as the crore rupees instrument, right? So here we can use again computer science methods like random forest, regression, some kind of way of mapping our low cost value to the high cost sensor value, where temperature and relative humidity are also inputs. And then knowing those weights or parameters, we can apply those for all low cost sensors in that vicinity, right? Where temperature and relative humidity are same, that same correcting factors should be applied, right? So calibration is very important in this case. So once we were already collecting this large scale data, one interesting thing we observed was in this particular case, this is a graph of a day like 23rd April, and this is the graph for another day, 25th April. And each of this timestamp goes on for 24 hours. So at 12 o'clock in the night to 12 o'clock in the next night, right? And what we see is each of these curves show a PM 2.5 value of one particular sensor. So this is a subset of sensors I'm plotting here, just for clarity. And what we see is all these sensors see some high value, and then they all come down here, possibly due to some wind or some rainfall, and then they all remain kind of at a lower value during the day. And in this other day, kind of all the sensors remain here, and then there is some peak here, and then they again come down, right? So what we discussed with the pollution control board is that if all these sensors spread across the city are seeing so similar values, then why do we need to sense more, right? Maybe the few sensors, crore rupees, which you are putting across Kolkata, they are good enough to capture the picture of the city, because anyway, the meteorological factors like temperature and humidity and rainfall and wind are so dominating there that they are kind of all the sensors are anyway going to sense the same thing. So why don't you cut down on budget and say, okay, a few sensors are enough, right? So we dug a bit deeper, and even in December, we found this, that actually there is a strong regional pattern, especially in a city like Kolkata, where all sensors, so this is on December 2nd, this is on December 10th, where spread across the city, many sensors report very similar values, right? But what we again going down, we when we debugged more, what we figured out was there are some sensors. Like for example, this pink line here, it comes at the top. So this pink line here actually belongs to this traffic intersection. So this is the green sensor which is here. So it always comes at a higher absolute value. So it might follow the pattern or the trend of the city, but its absolute value of pollution is always higher than all other sensors, right? So there is a very dominant local source of pollution here, which is this traffic intersection, which remains red across the day, right? And therefore, this is a what we call as a hyper-local pattern, that even though there is a strong regional kind of a pattern there, there are certain sensors which are always at higher values. And similarly, there is S18 here, which is near this water body, which is this brown line, which we found that it is always at a lower absolute value. Right, because being near a water body, because of the local winds, the particulate matter gets blown away, and therefore there is a local sink there. So even though there is a strong city pattern, there are certain places seeing always high pollution because of a local source, or certain places seeing always lower pollution because maybe it's greener, it has a water body. So these things are important for the pollution control board to know, that so that they can do more control at the sources and put more such sinks, right, across the city, which are actually working. Another kind of control they wanted to have was this strange pattern. So this is a particular sensor, and every day between a certain time period, its pollution shot up to say 800 or even 2500. It's like very high pollution value. So these are, we found that local economic activities. It might be a food stall, it might be some soldering or some lathering activity going on, where there is a local huge source which is coming up, and as a result, a sensor placed nearby picks up this daily strange activity happening, right? So these are all the kind of insights we can get when we collect data at large scale. And sometimes what we have figured out is combination of factors also are very difficult to catch. So this is a plot from Delhi, and the x-axis here has these sensors. Each of them is a sensor number. And before this dotted line, the sensors are placed in IIT Delhi campus, which is very green, it has less traffic. And beyond this line, these three are at traffic intersections. And we put them in collaboration with the traffic companies, which we were talking about. And this is a similar, this is November 14 data, this is November 18 data. And if we see on both days, the campus sees lower pollution than these intersection sensors, right? And the campus sensors are also sorted in an order where near the gates, where there is again more traffic flow, we see higher values. And predominantly what we see that, okay, traffic has some effect here as well, as we saw in Kolkata. But this plot has much lower pollution, less than 100. And this particular day on November 14th has pollution levels of 200. And this was funny because there was an odd even policy in Delhi, which said that odd numbered cards should fly on one day and even number cards should fly on another day. And this was particularly, the policy was there to control for pollution, right? And this day on November 14th, odd even policy was there, which meant that the number of private cars should ideally be in half. Whereas on November 18th, the policy was not in place, right? So there, ideally, the number of private vehicles should have been double. So we see some kind of a contrasting kind of a thing here, where we see intersection and traffic and those things are affecting air pollution. But on odd even, the pollution levels with less number of cars is double than a day when number of cars are more, right? So again, for this, we need more sensing. Okay, so this is not just one sensing one kind of information, which is just traffic and air pollution is not enough. And here the explanation comes from the wind speed in the city, right? And if you check winds, then on 18th November, which is a more car day, the wind speed is almost 3 times the wind speed on November 14th, right? And as we know, on wind, we as humans, we don't have any control. And that November 18th day, the wind came and blew away all the particulate matters. And if the wind was not there, then probably we would have seen some values near 400 or 500, right? So this is kind of something which is beyond human control. It is just in the meteorological factor, and we don't know whether the pollution will be less or more depending on that. Whereas odd even like policy is a human inflicted policy, and then we know exactly what kind of effects it might have. Right? Another thing is this, when we sense some information, this is also critical, that at what time scales do we compare sensed information? Okay, so this is an example again from the road, and we know how to put cameras and count cars, and at the same time we can measure air pollution at the same site. And what we observed is, repeatedly we have observed this, that when number of cars are very high, right, the pollution can still be very low. Again, this is counterintuitive, right? Because we repeatedly see that traffic intersections in Kolkata, in Delhi, everywhere, they give rise to more higher particulate matter. So what happens here is, at this time of the day, the temperatures are high, so the air expands and it blows up. And as a result, if you measure the PM at that point in the city, then you will get a low value. Whereas at night, when the air again cools down, it kind of comes down and settles. And therefore, if you live near the traffic intersection at night, you will see very high peak of pollution. Okay. So this is something which is very important when we build, for example, machine learning models to detect a factor that we don't match the timestamps exactly. There might be a delayed correlation with the factor. Okay. So by now, hopefully, looking at traffic and pollution, we understand that if we can build sensors and we can deploy them at scale, we can understand these phenomena as at much more depth. And then the pollution control board, the traffic control authorities, they can have more insights to work with, right? So this is good to have. And this is what my group has been working towards. Now, the problem is, this is the constraint number 3, which I want to talk about. We talked about constraints on the budget side, on the networking side. The third constraint is, of course, permissions, right? Unless we show them something like this, that you can understand this, before that, the government authorities don't understand the value, right? So they might be very unwilling to partner, especially with an academic institution, and therefore we had to run around a lot to collect this ministry letters, right? The Ministry of Earth Sciences, the Ministry of Air Pollution, across the different state governments and the national government, and this is a lot of work to do, right? So when we want to put a sensor on a public transport, then we want to go to the transport ministry, right? And even traffic signals and other places, these are critical infrastructure of the road, and we need proper permissions for this. So one way also of doing it, and this is something which might be useful, is there are also a lot of private fleets, right? For example, we were talking about Uber or maybe Swiggy, or and here they also have these large fleets which need not have this government permission, right? And we can also deploy our sensors there and go out of this red tape or bureaucratic issues which we typically face. So this actually happened, and I'm giving some anecdotal evidence here. And this when I was deploying sensors on the Delhi public fleet, there was this Ola Mobility Institute, but Ola cabs also had a large fleet. And they also said that, okay, we should be maybe putting this pollution sensors on Ola cabs, right? And something funny happened there. They had a data privacy concern. Okay, so this is again a topic where Professor Venkata, who is my colleague at IIT Delhi, will teach you a lot of cryptographic tools in the process of summer school. And this is not only important for security applications, wherein we want to keep our data safe and secure, but even in privacy applications. Okay, so this is also I wanted to touch upon a bit, because you are learning this public key encryption as part of the summer school. And this is a real problem which came to us when we were deploying our sensors, because what happened was this Ola cabs, they said that you cannot tell in a public data set where an Ola cab is located. Okay, so this is like a timestamp of the cab and the location of the cab, because they say that this is very private business information. If Ola cabs are not present at a particular moment near the airport, then maybe some rival company will send their cabs there for better business, right? Or maybe many of their cabs have gone on kind of a strike, and that will kind of show up in the data that there are very few cabs available now from Ola, right? So this was a strange thing, and we had a discussion that can we not give out this raw data. We need not say that this is the air pollution value and this is the location of the cab, but maybe we will just give an interpolated map of the city, right? We will say that, okay, we do spatio-temporal interpolation. We say that these are the grids in the city, and based on whatever sensors we have, we will give the mean values in those places. But the problem is, because the number of sensors are varying and they're moving, we also need to give a variance value, right? Which tells with what confidence is that mean being given. So if you use some Gaussian process regression or some machine learning tool like that, it also has a variance which the model gives up. That at this particular point, this is the mean pollution, and this is the level of confidence or the variance with which I'm giving. And as soon as we look at the variance plot, again, the location of the cabs become very apparent, because where cabs are present, the confidence is very high, and where cabs are absent, the confidence is pretty low, right? And the privacy does not go away. The privacy problem does not go away. So one of my PhD students, Ismi, actually used some cryptographic tool. And this is a generic problem that if there are different companies, like say Ola, Uber, Swiggy, which have some nice data that they have collected, and the pollution values itself is not privacy sensitive, right? Pollution is a public information and everyone should be able to see that. It's only that latitude, longitude, and the timestamp of the cabs are the privacy sensitive parts. And therefore, there are tools called privacy preserving machine learning that can we say, okay, we can query pollution, we can ask for minimum values, maximum values. So this is for all these clients, they can ask for these that over a city, what is the minimum, maximum, average, which is the least polluted route to go from one place to another. We can ask all sorts of queries, and we can also build a lot of models. We can say tomorrow the air pollution will be this, and you train a machine learning model, but then the different companies don't share with data with each other, right? They hold on to their values. And then there is something called secure multi-party computation, which they do, which preserves the privacy of the data, but trains the model jointly. Okay, so this is one way of doing this. And of course, there are alternate ways, and the PhD student evaluated whether that is an alternate viable option. So for example, adding differentially private noise is an option, that at every location add some noise. But the problem here is we are building our sensors, we are calibrating them against high cost instruments so that their errors are as low as possible. And then if we start adding noise, then the utility of that sensing goes up, right? So differential privacy might be very useful in many scenarios, but for something like pollution sensing, where the sensed pollution value is so critical to be correct, it's not a good thing to do, right? Then there are other questions which are a little bit more mathematical in nature, that suppose every location in the city has a different confidence, right? It says that this is the mean pollution and this is the confidence here. This is the mean pollution, a different confidence there, because the number of sensors around that place is different. Now, if someone asks a query and says that what is the average or what is the minimum across many such locations, then what should be the confidence for that answer to that question, right? Because each of those constituents have a different confidence. Something has 20% confidence, some has 50% confidence. Then what is the answer to an average query, or what is the answer to a minimum query? That this is the average of all these values, and this is the confidence in that answer, right? And this is typically called error propagation. And to be able to compute that error or that confidence, that particular function needs to be differentiable, which is not true in some of the queries. For example, minimum and maximum in their typical form, they are not differentiable. And therefore, ISMI, my PhD student, had to find some approximation to that function, which is differentiable, right? So those answers can be queried. And then a lot of work goes also in designing, as I said, if you want to train machine learning models in a privacy preserving manner, then the model architecture is also important, right? What kind of neural network layer has less multiplications versus more additions, which is easier to do in cryptography, right? So because when we ask a machine learning person, for example, here the x-axis is a model architecture, which are the number of parameters in a model, and the y-axis here gives the error of the model. And if you see these blue dots, all these models are of similar size and they have similar RMS, right? Similar errors. So the machine learning person will not really care about which model one chooses. But if we ask the cryptography person that what is the model to choose, they will say that these models seem to have a lot of matrix multiplications, which kind of blow up the latency of that model in the privacy preserving domain. And therefore, probably you should choose something here. Right? So this is a trade-off space which only happens when we look at machine learning and crypto together and not in isolation. And finally, this is also, as we were discussing, that not just algorithm in the space of ML or crypto, but actually which compiler compiles it, which runtime software actually manages scheduling and other things, and actually which hardware. That is it a CPU or a GPU, and how the function is mapped there, right? So all these play a role in performance. So here, for example, I will just pick one graph, for example, the average query, and the x-axis is the longer a query, right? So if this says that an average over say 400 grids in the city. And if you look at this red line, this y-axis is a time, right? And how much time this takes. So this is the circuit evaluation time. So we see that this red is much slower than the blue, which is funny because the red comes from very recent papers called this arithmetic, Boolean, and Gauss combined circuits in crypto, ABY circuits, which says that you should express your functions as arithmetic circuit or Boolean circuit or Gauss-Garbel circuit based on the function itself, right? And in theory, they showed in the paper that this is much more efficient than this blue curve, which is simple Gauss-Garbel circuit. But when PhD student Ismi, she evaluated this on real hardware, she found that the Gauss-Garbel circuit, which comes from the 1980s, is many times faster, right, than something which is theoretically faster. This is because of this, again, this full stack, that something might be algorithmically very good, but because the libraries, the compilers, and the hardware have not been optimized for it, you don't see that kind of advantage actually translated, right? And there is a lot of gap where, again, researchers and engineers can work on to bridge this gap. So overall, summarizing my research, there is budget constraint in developing countries like India, and computer science can help allocating this budget carefully. Where to put a sensor, right? Where is the regional pattern? Where is the hyperlocal pattern? Where should we put a crore rupees instrument? Is something which computer science can solve as an optimization problem first after collecting this sensor data, which I have been describing, right? Then this network connectivity problem that don't send every raw data, videos, everything in real time to the cloud, but try to process in situ at the different roads of the city as much as possible. And then the compressed information, whatever is really needed, then send it to the cloud. And then thermal safety, that when the temperatures are high, the edge platforms should not fail, they should not reboot continuously, and the permission issues and the data privacy concerns. And typically, me and my group have been working on these different constraints using computer science tools, right? So if we look at our undergraduate courses, right, what I teach in the class or what I have learned myself, there will be, of course, computer architecture, because a lot of these embedded devices I'm building, I need to decide on the microcontroller or CPU or GPU or accelerator, what memory interface to use, and things like that, right? And operating system is something which is, again, at runtime, this is very important for management of the resources and the thermal safety, for example. Parallel programming is especially with GPUs and with FPGAs, CUDA, and all those kind of APIs become very important, because as we do more heavy computations, either in the cloud or at the edge, then being able to do something parallelly, utilizing very important. And then on the security side, understanding that what can hackers do, how to secure the platform, then the machine learning aspects of it, applied machine learning, not understanding the theory of it, as probably Jatin will be able to teach you in much more detail, but at least being able to know that what computations are happening and how can they be more optimally done, right, at the edge, is something in the computer science domain. And then because I work closely with the traffic or air pollution domain, there will be people who tells me that this is what wind does to air pollution, or this is what temperature does to air pollution, which is a domain knowledge for them, right? And I am collecting data, I'm observing something, but for the explanation of it, whatever my machine learning or my model has figured out, I will need to go and go to them for sanity check so that they can help me understand better. Right. So this is kind of what we call as interdisciplinary work, that within computer science, there is not, I'm not an expert where I only write papers in computer architecture. And that's a very, very, very nice thing to do. So you will find computer architecture architects in IIT Delhi or in other places who only write computer architecture papers, right? But when I work with the real world, I cannot just say that I will only focus on architecture, because then if I don't understand the security aspect of something, then the privacy preserving ML will not work, right? So there are two kinds of researches which people do. One is something going deep into a computer science domain, whereas someone like me doesn't understand maybe something in quite that depth, but they understand it enough that they can make these different things work together. Right? And since this is a Vigyan Vidushi talk, I really wanted to emphasize this point, that like we as women, we see gradually reducing people, right? So that's a different kind of a sensing that we do, that in schools versus when we go to undergrad versus when we go to postgrad versus maybe when you go for PhD, postdoc, we become a professor, then the number of girls we see around us gradually keep on declining, right? And I mean, one of the reasons I'm not there in person in TI for today is because I have a 2-year-old daughter, right? And I was afraid to carry her in this Mumbai rains and get stuck in traffic there, or the flights will get delayed, right? So that's the reason you don't see me in person there, even though I had bought the tickets. So this is something which I would really encourage you, be it you do theoretical stuff or applied stuff or whatever, that now in 2025, make these friends at the Vigyan Vidushi event. And then 20 years from now, 2045, you look and see, where are those girls now, right? Are they still doing something? It doesn't matter whether it's in theory, in practice, in some form, right? In some form, have they been able to continue or not? And this is where I would like to end my talk and take questions. Thank you.
Thanks, Rijurekha. Questions? You will need a mic if you have questions.
Am I audible?
Yes.
Yeah. So I was just wondering about the sort of privacy concerns that, for example, Ola, etc., have. Is it more about privacy concerns about sharing the real-time data, or did they just not want to share GPS information at all, or anything identifiable, even though this may be, I mean, like, let's, for example, we wanted to understand some historical sort of we see in pollution data or something. I don't particularly care if it's happening in this particular hour, but I might
Right.
understand patterns. Was that also a problem?
Yeah. Yeah, I think real time is very problematic. And even historically, they would. So, I mean, even if we build something privacy preserving, you know that with private companies, they still might not agree to share their information, right? So, it was more like we go back to academia, we say there is a way of doing it, but still it is still in their hands that whether they will agree and say, okay, there are these different companies, we will take part in this crypto protocol. So, but the discussions we have been having with the Ola Mobility Institute, which was being coming up at that time, they say that real time and even historically, so they have these various issues that how this since these are app based driving platforms, that exactly actually how many drivers pick Ola versus Uber is also something proprietary for them. So they don't want even historically to show that they have been maybe in the month of January or February or something, they had very few cabs. Which is kind of bad kind of reputation for them, and maybe Uber has many more cabs. So in general, I found them to be very very kind of I mean they came forward themselves. It's not like we went to them. They say that we want a good name, we want to put some sensors in our cars, but then they were kind of stuck in this point of number of cars, location of cars, real time. Historically, these are very private for us. So one way, of course, they can say that we will keep everything within our domain and we will give out pollution maps in the city. That's also feasible, right? So whatever models we have built, whatever sensors we have built, they can adopt it internally and say that, okay, Ola itself will do everything. You query us, we will just give you answers. So that's, I guess, one way of going forward.
Good evening, ma'am. My question is these components that you attach to cars or even buses, are these components prone to attacks like tracking of the cars or even location of a person? Because, like, I read a case study of America that some cameras were getting used by some people to track their partners and where are they going. So, what are some mechanisms that you implement in those components to protect it from these kind of attacks if they're prone to it?
Very nice. So the funny thing, you know, that in any country, you will ask that what are the rules, right? So, for example, I am putting up this sensor, and it is very funny that in India, for sensors, there are no rules of who is collecting the data, where is the data being stored, what is it being accessed for, right? If you see even now, right, we use the DG Yatra app. Or any Arogya Setu app when COVID happened. Do we know actually that where is the data, who accesses the data for what purpose? So there is, when even I put up these sensors, the only test kind of standardization test I had to do, that it does not catch fire or it doesn't interfere with the bus's electric circuit, right? That's a physical test I had to do. But nobody actually did a penetration testing of actually what software is running on my platform. So in general, in India, these kind of sensors and these might be very, very vulnerable. That if maliciously or even unintentionally, I can put up things and that might be actually sending the pictures who it is not intended for. It's not the traffic police that is getting that. And yes, there is also, so that's something which I didn't cover. There are many people working on it. That how do you ensure that, first of all, how do you verify software? It is becoming very, very difficult with ML models. That how do you guarantee that an ML model is doing exactly what it is claiming to do? right? Maybe it is detecting, of course, number of cars, but maybe it is also detecting my face, right? And how do I, so there has to be some kind of an audit of a machine learning model. And if suppose someone is honest enough and say, okay, you can audit my model and see what is the output, but then to make sure that that model actually is running in real time and not something else, right? So this is what we call as computational integrity. And you can do it in different ways. Again, there are techniques. So you can use hardware security, where you have some secure memory, something in from the architecture you can use, which is kind of doable, but again, it is difficult to do for every application. They might not have access to the secure hardware on a platform. There are software ways of doing it is maybe just simple hashing, that periodically you hash the software you are running, and you also have something called a gold hash. So this is called attestation, that you attest that, okay, I have a gold hash, this is what should run, and periodically I'm hashing and comparing that these two are matching, right? But the more concrete way of doing this is this zero knowledge proof kind of thing, where you actually, if you can build a pipeline where computation is happening and it is also generating proofs for every step that this is actually the computation I have done on this input, right? So ZKP is again a very strong cryptographic primitive, and some of you can work. So one of my PhD students, Mehreen, has been working on some smaller models and networks to do ZK proof for, because it's a cryptographically heavy kind of machinery. So there is a lot of scope of work to make these more practical. But as you say, audit and security of these platforms are very, very important.
Thank you so much.
I have a question. So sometimes in these discussions in popular press, when we talk about sort of upcoming technology, and when we read about views of policymakers to bureaucrats to people in the judiciary, people in audit agencies, it feels like there's something fundamentally that's missing, and this happens quite a bit when we talk about things like security and cryptography. And differential privacy also feels like a technology like that, which would be hard. It's almost unbelievable that certain things that we can prove is actually true. So how difficult are these conversations with when you talk to people in the industry about this?
I mean, even as I was saying, that security comes maybe a bit later, even without showing some real value. For example, this, when I say I can give challan to vehicles and it will generate 200 crores, the agencies will be very happy to pick it up, right? So it depends on, but as soon as I say that for security, we need some special hardware, we need some extra computation. So this is also, even the companies who are working on ground, they might not have budget for security, right? So security should come at zero cost in some sense, that, okay, we should, it's just like the bigger companies themselves, like Facebook and all, they kind of give us this long list, and then when something wrong happens, they say that, okay, yeah, some leak happened, right? Because industry in general, they are, so that's where I think formulation of these GDPR kind of laws, Europe has been showing some way. And in India, I have not seen, as I was saying, any kind of standardization, right? And this is something which someone in IIT Delhi is trying to do in a different space for very large scale public data, like for this election kind of data or something. So Professor Subodh Sharma is someone who is at least having some dialogues of kind of, because every domain will have its own challenges, and he is trying to see at least for some places, is there like some auditability of where the data is being stored and access control by which authorities, because these seem like my every boarding pass at every airport with my face is getting stamped. This is a huge amount of data which is being generated every moment, right? And as citizens, we are kind of, if there is no DigiJatra, the queue is very long, right? It's for us, it's a convenience thing. We all start installing it, right? Even though we, as privacy aware person, maybe initially I would resist, right? But then with a child, that becomes a natural thing to do. So I think you are very correct that they would just say we are doing it. It's correct, right? And understanding the technology, we know how hard it is to do it, right? And unless these questions are being asked as Subodh is trying to ask, and even in the IoT space, in this traffic space, sensor space, I have some, but still it's not a lot. So it's gradually building up this reputation of doing some real work, I would say, that over the last 6-7 years as an assistant professor, and then people would know, and then maybe I can say that maybe this is a security measure you should be taking. So it's a long way in terms of awareness, and even the public data, they are not just aware. They don't know where CCTV cameras are, what is it being collected for. So it's a very, very huge gap between differential privacy papers and the ground.
So the sensors that you use, like you mentioned for particulate matter and so on, how many of these are off the shelf and how many would you have to custom build, custom design?
Right. So mostly from the earlier ones, as I was saying, first prototype, we would get some PMS units from China, but then again, importing sometimes becomes difficult. So thankfully in IIT Delhi, we have a Sense lab and we have a maker space. So, and these are not very, very difficult to build, right? So if we can get something off the shelf at a reasonable price, I would actually bring those components in, right? So for example, microcontrollers and those we don't even make in India, right? So SD card, 4G radio, the modem, those things, whatever we put together. So it's only when there is some restriction on some component that we will actually make, and then of course the PCB which holds everything together, that will build in IIT. And it's sometimes good to have a small company. We have something called Aerogram incubated in IIT Delhi, because this hardware and ordering bulk hardware, that sometimes becomes problem as a professor. So having a small company, which also might have some small business opportunities, is good to have. So yeah, we started with the pollution control units from China, PMS 5003 and 7003. And then from second year onwards, we started making it. It was cheaper as well as more reliable in terms of import ourselves.
Hi, ma'am. Thank you so much for the talk.
Thank you.
You're using low-cost sensors for collecting data. Have you ever felt the need to fetch any more open source data, like maybe from GIS or anything else?
Yeah, I mean, if people make things open source, that could be very good. But as I was saying, people have privacy concerns and other concerns. So yeah, I think pushing for open source data and open source code, verifiable code is should always be, at least in the academic domain. We should push for that. And whether companies would agree to it or not, that's a different question. Yeah.
Good evening, ma'am. Ma'am, what do you think is the main reason we don't get permission from the government for these sort of things? And if we get permission from Ola and Uber, if they are sharing their data with us, so why are they doing this? Like at what expense?
Government can do that. So the one thing is, where does the budget come from? So that we'll have to. There is generally, so when I say government needs to give permission, they have to see some value in it, right? So it should not be. And of course, the bus companies themselves are very busy. right? So the the Mumbai trains, it's a very busy network. So whatever extra we are doing on top of them, it should not hamper their workflow, right? If I say that I'll do some testing in some buses, then the bus should be able to leave the depot at the correct time and come back at the correct time, and the people should be able to get in and out. So I think the permission part is definitely needed, that someone just doesn't go and waste their time. So that's very important. This private companies, like they already have. So for example, with the Google Maps, which we are using, they are so accurate because all across the world, everyone is using these maps, right? And it's a crowdsourced information. So we already see the value in numbers, right? And Google is an aggregator company. It's of course, it is giving a much more maybe accurate API to Uber or Swiggy or some corporate, but it still gives us a very good enough value, right? Even as a lay person, without paying anything to Google Maps, when I ask the travel time, it gives me a good estimate, and that's private data, right? So it's not like the private companies are not giving it. And of course, with this huge user base, they are showing the value of it. And once there was a lot of free usage of Google Maps, then these delivery companies, Amazon, everyone started using it as a paid service, right? So they would, the Uber or other companies, they would have to buy it from Google Maps to integrate it in their app, right? So I think I think the models, when in 2005 or 6, when MIT Hari Balakrishnan was starting this field, he also did not know the incentives or the financial mechanisms in place that would come in. But I think the market has evolved, and even now in our cities, if you look at a smart city project, these will be like multi-100 crore tender which go out, right? It's not like the budget is small in that sense, but then it will get divided. And I have been auditing these kind of tenders quite a bit in the last few years, and you will have to see that how much money have they put for network bandwidth, right? Maybe they say they don't think that is important, and then the system does not work because there are these cameras on the road which are taking pictures, but they are not sending it anywhere, right? Because they did not put in fiber optic. So sometimes the government also, the audit, a technical person has to be there, and someone like Larsen and Toubro or some large company actually wins these bids and then gives it to the smaller companies. Some of them does traffic, some of them does something else, and then everything has to come together. So I think there is enough money on the government side, enough incentives on the private side. But sadly, our cities are still not that livable, I would say. So there is a lot of scope of work on both spaces. But there are economic incentives. It's not like it's a loss thing that putting out a sensor is a kind of completely money gone for waste, right? So there is definitely value.
Ma'am, so do these private companies want something in return, or they just usually share their data like that only?
So it can be a paid API for them, as I was saying, that Google, when it gives the travel time information, it can give it free to some people and a paid API to some other people, right? So it can be actually money, real money. If, for example, the air pollution one, which Ola or Uber, Ola was talking to us, that can be some kind of a CSR activity. So companies also have to do this corporate social responsibility, and they have some funds for that. And they want this publicity in newspaper where they say Ola helping Delhi pollution or something like that, right? So it can be a different incentive in that way. So, but they won't want money from a professor, for example. I mean, that's definitely not there. But that might be their incentive of taking part in something which gives a good name to the company. Other than money itself, they can even earn some money if they can monetize it, right? If there is some data they are collecting which is valuable, they can create a paid API and to earn money.
Okay. Thank you.
Thank you.
Other questions? Okay. If there are no further questions, let's thank Riju again for a wonderful.
Thank you. And sorry for not meeting in person. Yeah. Bye. Take
Okay.
care.
Thanks.
Thank you.